Welcome to the sixth part of my series on the Lucas Lehmer Primality test. Today is a big video, unless I decide to split into multiple videos. Regardless, it's cool. Alright, so today we are going to prove that if the Lucas Lehmer Primality test says a number is prime, that means it's prime. Okay. So, and then the second part will be if the Lucas Lehmer Primality test says a number is not prime, then that number is not prime. But that's not what we're proving right now. First, we're going to prove if it says it's prime, it's prime. So, let's get started. Okay, I think I have enough paper here. I may not. I may have to get paper later. I don't know. Okay. So, if you remember, yeah. So we defined the Lagrange, theorem. Like we sort of showed what it says, and then we proved it's true. That's what we did in our last video. So we will be using that in this video. This is a pretty complex video, so yeah. Okay, so first of all, assume. Okay, so we're gonna be using a lot of stuff in this video. All the stuff we've learned in all the videos, I think. Not that. Well, actually, yeah. Maybe. Yeah. Okay. Anyway, so assume that. So what we want to prove is that if the Lucas Lehmer primality test says a number is prime, then that number is prime. And that is our goal. To prove that, assume that the Lucas Lehmer primality test says a number is prime, and that number is not prime. Okay? And we are going to prove a contradiction using this. So that is what we're going to be assuming for the entire video at the end, or the end of the next part if I decide to split into parts. We will end up showing a contradiction. Okay, so if the number is not prime, the number that the Lucas Lehmer primality test said was prime, that means it has to have a divisor, okay? Let's call like a divisor of it. Let's say the smallest divisor, which it has is Q. Now I'm not completely sure if this is necessary for the proof, but Q must be prime, and the reason for that is because if it wasn't prime, that means it has smaller divisors, which would then be even smaller divisors of our big number. The 2 to the whatever our Mersenne number that we're trying to prove whether or not it's prime. The smallest divisor must be prime, because if it wasn't, that means there's an even smaller prime divisor. So, yeah. So just keep in mind Q is prime. It may not matter, whatever. Okay. So we know from the definition that there has to be Q is 2 or larger. Okay. Meaning, so therefore, we have a number Q which divides our Mersenne number. Okay. And this number is a prime, and it's 2 or larger, right? Because we choose the first one, bigger than 1. Okay, so therefore, what we're gonna do is we're gonna construct a group. That's why we talked about group theory in the last video. This is sort of a group theory proof. Okay, so assume I write down all the numbers, okay, that are in the form of. So do you remember my example with modulo 5, where like you had 0, 1, 2, 3, 4, right? So in this video, we're going to do something similar, where you have modulo q, which means you have 0, 1, 2, 3, 4, all the way up to q minus 1, whatever that is. Okay, so that's our group. Except we're going to have a, right, plus b times the square root of 3, where a and b are one of those. So like if q's 5, that means a could range from 0, 1, 2, 3, 4, so does b. So a valid number could be 3 plus the square root of 2. It's basically, no. 3 plus 2 times the square root of 3. So it's basically any number between 0 and q cannot be equal to q, plus any number between 0 and q times the square root of 3. Okay, so this is our group. Well, technically it's not a group, but we'll talk about that. So yeah, so how do we define multiplication in this group? So if I have some number, right, in my group, say I have some sort of number, right? This is my number, a plus the square root of 3 times b, for some a and b between 0 and q. C plus the square root of 3 times d for some c and d between 0 and q. Okay, so when I multiply them, if I just normally multiply them, it would get too big, right? Like maybe the new the new number next to the square root of 3 would be larger than q. So what we're going to do is very similar to what happens when we multiply or add numbers normally in modulo. Like if I was doing modulo 5, like the remainders when you take away 5 repeatedly, when you divide by 5, what I would have is I would end up basically, if I had two numbers and to multiply them, I multiply them normally, and then I take the remainder. So, like if I was doing modulo 13 or something, and I multiply 5 and 9, that would normally be 45, and then we take the remainder when divided by 13, which would end up being 6. Okay? So, it's a very similar idea where for our new two numbers, we're going to take the remainders. So normally, so first of all, I'm going to get to that, but normally it would just be, I'm gonna like do all four parts. I'm going to expand this out. Okay. Alright. So what I have here is I expanded this out, right? Also note this is a B, not a 6, so it's not 36D, it's 3BD. So I expanded this right here out. So now what I'm going to do is I'm going to group it. Okay, I'm doing this right. Let me just double check. I don't want to make a mistake. That would be bad. Okay, I don't think I'm making a mistake. So give me a second. Yeah. Okay. So in real life, if you were to multiply these two numbers, this is what you would get. But remember, we're dealing with modulo q, which means that what we want is both of these numbers, this new number and this new number, they have to be smaller than q, which means we're going to take the remainder when you divide by q of this number, and the same thing for this number. So when we end up, so what we do to multiply two numbers is we multiply them normally and then take the remainder of this modulo q, or when you divide by q, and the remainder of this when you divide by q. Alright. So now what we have is we've defined, and note that if I multiply any two elements in my group, remember in my set, sorry, if I multiply any two elements in my set, what that means is that basically what it means to multiply any two elements in my set is those two elements must be, when you multiply them in this special way, they're going to end up being in the set. So it has closure. And the reason for this is because if I multiply any two, it's going to be another one in my set. And I just defined multiplication down here. So now what we have is, let's look for elements. Remember another property. Also, yeah. So another property is that if I take A times B times C, it doesn't matter in which order I do them. And yeah, it would be a nightmare to write that down and all. But it is quite easily proven. Yeah, they're basically like, it doesn't matter in which order you do them because we're dealing with modulo or remainders, and that number matters with that. So next property is identity. Now, this thing that I just defined, this set, that's why I'm not calling it a group, is not a group because not every, sorry. There is an identity, but not everybody has an inverse. Okay, the identity would be 1 because any number multiplied by 1 normally, and in this special group, or sorry, in the special set, because it's not a group, would be itself. So the final property we need is invertibility, okay, which means every number has to have an inverse. Right? Well, some numbers in a set do, right, and some don't. So let's list some numbers that don't. Okay, well, I'm just going to list one of them. 0. 0 does not have an inverse because in real life and in this special group, 0 multiplied by anything will be 0, which is not the identity. The identity is 1. Therefore, 0 has no inverse, so therefore this thing is not a group. Alright, so what I'm going to do now, so I'm going to call this sort of set I defined, where it's A plus the square root of 3 times B for any A and B between 0 and Q, right? Alright, I'm gonna call this X, okay? So I'll write that in a second. I'm just going to show you again. This is for A and B anywhere from 0 to Q. This is an element in our set. and I can multiply it by another one, and then take the remainders, and then I get a new element that's also in the set. Alright, so, and then the one thing that's stopping this from being a group is because it does not every element has inverses. Okay, so I'm gonna take X. Let's call this X. Note that X is not a group. Okay, because it's not a group because basically the problem with it, not everybody has inverses. Okay, so and then I'm gonna find out how many elements, how many numbers are in X. So, well, remember we defined X as the set of all the numbers between 0 and Q, not including Q, so it can go up to Q minus 1. So for any A and B like that, A plus the square root of 3 times B. So therefore, there's 0 to Q minus 1 Q choices for A and Q choices for B. We multiply them, and therefore we get Q squared. So the number of elements in X, our group that, our set that we've just defined, not a group, is equal to Q squared. So to write the number of elements in, it's also called the order, and we write the absolute value of. So I'm going to write right here the absolute value of X equals Q squared. This means the number of elements in X is Q squared, where Q is the sort of number where we define when we take, it's always the remainder. These have to be between 0 and Q, and they cannot be Q. Okay, so next what we have is I'm going to okay, so now I'm going to define this new thing, X star. Okay, and this is going to be exactly the same as X, except it's only takes the elements that do have inverses. So if you remember, it still has the 3 other properties we talked about: associativity, and it has identity element, and it has closure. Okay. So then the one thing, actually, yeah. So basically, and then it adds the 4th one because we just defined that only the elements that have an inverse will be in this new set. And now it's a group because it has all 4. So X star is a group. Okay. Now how many elements are in X star? Well, those are just the elements of X minus all the elements that don't have inverses. Well, we know there's at least one element in X that does not have an inverse. That element is 0. So therefore, it's the number of elements in X star is equal to, is less than or equal to the number of elements in X minus 1. That's a badly drawn 1, but okay, because there's at least one element that gets kicked out for not being a invertible, which would be 0. And then we figured out the absolute value of X is Q squared, or the order of X is Q squared. So therefore, this is Q squared minus 1. So therefore, the number of elements in X star is less than or equal to Q squared minus 1. Okay. So let me think. What do we have now? Alright, so now we go back to some stuff we talked about, I think, earlier. So remember, we have our number. So if you remember at the beginning of this video, what I said is like we are going to have this number, a Mersenne number where the test says it's prime and it's not prime, and then we're going to prove a contradiction, meaning if the test ever says it's prime, it is prime. Okay. So therefore, what this means is we're going to call that number, let's say, 2 to the n minus 1. Okay. So here I'll show you. So I have some number 2 to the n minus 1, right? And that means, so therefore, yeah. Okay, I see. Sorry. So because remember we defined Q, because 2 to the n minus 1 is not prime, because we're going to prove a contradiction assuming it's not. So we assume it's not. That means there must be a divisor Q, right? Where Q divides 2 to the n minus 1. Okay? And therefore, and also remember that we figured out the test is going to say that it is prime. And remember, the test was to check, does it divide s n minus 2, okay? So this right here, this was our test, okay? So the test said yes, but the primeness in reality said no. This can never happen, and we're going to prove it's impossible. So, but we're assuming this for this video, and maybe the next one if I decide to make a second part of this specific topic. So therefore, there's a Q divides this, which divides this. So therefore, Q must divide this. Okay, let me see. Is that did I do it correctly? Yeah, I think yeah, I didn't need to do that the third part actually. So we didn't. Although it is true, I don't think we need that part. Right here. So we don't need to see that Q. So we know that Q divides this just. So I didn't really need to do that part. It's just an extra fun thing to know that Q divides that. But you know what? So Q divides 2 to the n minus 1, okay? So what this means is that, right, because that's how we define it, Q is the divisor of that. Right. So therefore, 2 to the n minus 1, it's like, yeah. And again, I started checking Wikipedia to make sure I don't make any mistakes or stuff like that. So, yeah. What? So therefore, 2 to the n minus 1. If you remember our group that I defined, I'm trying to be a little quiet, please. Okay. So basically, 2 to the n minus 1. It is divisible by q, which means in this sort of group we defined earlier, it would be congruent to 0 modulo q, because its remainder is 0. So it's sort of like 0, right? Yeah. Alright, so now we have that this is true, okay? And now if you remember a long time ago we defined our numbers W, right? And W bar, and those were 2 plus the square root of 3 and 2 minus the square root of 3. I'm going to focus on W because I don't think we need W bar for this, but so basically notice that W, okay? Notice that W is it basically is an element of our set X of X and X star, okay? Because it does have an inverse. W bar is its inverse, as we talked about, because when you multiply W and W bar, you get 1, okay? So therefore, what this means is W is going to be in X star, okay? So W is one of the elements. Alright. So basically, yeah, so if we multiply 2n minus 1 by W, right, is that what I want? Yeah, so therefore, because we can multiply, like, what we can do is we can multiply W, like, as high as we want, sort of. Like, if W's in our X star, right, that means W times itself is in X star, because any two elements in our set, even if they're the same element, when multiplied must be in the set. And I can do the same thing and I repeat it at W cubed, W4. So W to any whole number power is going to be in X star, okay? So therefore, if I was to choose that exponent to be 2 to the p minus 2, so W to the 2 to the p minus 2, so I'll show you right here. This right here, this is in X star, okay? Because of what we just talked about. So therefore, so yeah, let me think this through. Yeah. Well, so what this means is that, alright, so this element, so if I was to multiply, so this element right here, technically it's not in X star because it's like too big, but it's equivalent to 0 because its remainder modulo Q is 0, okay? So this is sort of like 0, right? And this is just some element, and it applies also in this one that anything times 0 is 0, okay? So therefore, 2 to the n minus 1, which is 0 in this set, times W to the 2 to the p minus 2, which is just some random element, that has to be equal to 0. And when I say equal to 0, I mean equal to 0 in the set that we're talking about, okay? Which is X star, okay? So Therefore, and I'm just gonna multiply on k is just some like integer, right? Yeah. So k is just some integer. I'm gonna multiply on here. This is 0 already, so I'm multiplying by k when k is a whole integer or whole number won't do anything. I'm just adding this repeatedly, so it's still 0. So I can just multiply both sides by k, and it's still 0. Alright. So now I have this. So this may look a little familiar to you. Yeah. So basically, if you remember, right? Okay. So right here, this right here is right equal to, yeah. I'm just double checking I didn't make a mistake. So if you remember from our first formula, here I'm gonna show you my first or our first formula was that we found was w. I think this was in the third video, the one before this. Right. So if you see right, sorry, I think I'm focusing. Oh yeah, sorry, it's over here. So we had this formula. That's what we derived. Okay. So if I add 1 to both sides, right? So actually no, I won't do that yet. So this formula still sort of applies in our new group. So we know that it's equal to 0, right? And then this is also true, right? So therefore, we can sort of substitute this formula into this one. Okay, remember this is the formula we got in number 3. This is the one we were just talking about, and this only applies in the group X star. So what we have here is that, alright, so these two are identical. This one right here and this one right here, those are identical. Also, I may have switched from a P to or from into P. Yeah, so I'm gonna fix that. It's because Wikipedia uses P for a reason I'm not gonna go into, but okay. So therefore, because this is true, right? This is 0 in the group X star. This is just 0, right? Meaning that this thing right here is 0 minus 1 is just -1. So this in the group X star is -1. Okay. So I'm gonna write that down. And remember, this is only in the group X star. It's not really in reality -1. Okay. So let's see. Got this. Alright. So I have this one, right? And then if I square both sides, then I get, well, the right side, -1 squared is just 1, right? And then you've probably seen this before, so if you just remember, the 2 comes down here, so it's 2 times 2 to the n minus 1 is 2 to the n, so w to the 2 to the n is 1. So let me write that down. W to the 2 to the n is 1 in this group. Okay, so I think I don't want to make this video like an hour long or half hour, 45 minutes or something like that. So I think I'm gonna stop pretty soon. Let me see. Is there anything I want to finalize with? This video. So yeah, so we have this and this. So basically, I think what I'm gonna end with in this video is in the group X star. Sorry, do I have this tilted? This right here is -1, and then when I square it, it's 1. Okay, and we're going to come back to this, and we are going to get a really nice proof that if it says it's prime, it's prime. So thank you for watching. I hope you enjoyed the video, and goodbye.